All right. Hey, Honors Chemistry. So I wanted to make kind of like an audio track to this slideshow. I talked about this slideshow for the second half of the week last week. So some of us may have been out, or if we want some extra support in understanding, keeping track of energy change, I would watch this video. So something that we will see eventually is I have an initial chemical energy, and I'll represent that as like 2 bars. We're just going to keep it with 2 bars to make it simple. If you remember, there are 3 different types of energy accounts. There's thermal energy, which is for things that are hot and cold. Phase energy are for phase changes, and chemical energy is for energy required or released in a chemical reaction. And so what we'll see that we'll have energy that's going to be added to or released from our system, and it's going to change our chemical energy initially and finally. And initially, it'll be our reactants. Finally, will be our products. Okay, so this is not how you're going to be doing your LOL diagrams. This is just an overall example. So let's start by looking at endothermic reactions, which is what we did on your worksheet number 4. So an endothermic reaction, you're going to have to recognize this on your unit test, and you're going to have to recognize this and on your final. If energy is a reactant, it's going to be an endothermic reaction. This is because I need to add energy to my system in order for it to go. Endothermic is the energy entering a system, or energy is going into a system. So if you remember that from like way back in unit 3 or 2, endothermic reactions are energy going into the system. So energy is going to be a reactant. Also, if I have to add energy to my reactant side, that means my reactants are going to be lower in energy to start than my products. My products have absorbed all of this energy and it's not going anywhere. So my products will be higher in energy. And because of that, this is what our energy diagram looks like. I know some words cut up, but it's okay. This is an energy diagram, also known as like a chemical potential energy diagram for an endothermic reaction. My reactants are lower in energy, and then it goes up to my products that are going to be higher in energy. So this is going to be an endothermic reaction potential energy diagram. And so if I ever ask for, and you'll see this will be on your unit test, this is going to be on your final, where you have to recognize potential energy diagrams for endothermic or exothermic reactions. So again, for endothermic, my reactants are lower in energy than my products. They absorb energy. So I would sketch this, and I would sketch this in the previous equation into your notebook. So for thermal energy, a couple of things are going to happen. You could sketch this in your notebook too, but we need this energy to be absorbed. Energy is going to be used to make the molecules move faster. Remember, if I absorb energy and things get warmer, they move faster. And if I don't have enough energy, the particles aren't going to come together and form our product. So you could write those 2 bullet points in your notebook. And so here's how we start. This is going to be the very beginning of your LOL diagram for an endothermic reaction. So this is like when you did the sodium bicarbonate in the test tube. It was that solid in the test tube, and you put it over the fire. First, the test tube gets hot. So I start with some thermal energy and some chemical energy. We got to remember from like unit 3 or even unit 2 or 4, I cannot have 0 thermal energy. Matter doesn't exist. Same thing, I cannot have 0 chemical energy. Matter wouldn't exist. So I have to have some. You could have 1 bar, you could have 2 bars. We're going to keep it with 2 bars. I'm going to heat it up, right? It says something about I heat it up, or I put it over the fire, not burn in air. I say I heat it up, or I put it on a hot plate, or I warmed it up in some sort of glassware. If I do that, my thermal energy increases, right? So energy is going into the system. This is showing me how it's an endothermic reaction. In an endothermic reaction, energy goes into the system first. Then my second part, so this is kind of like what I'm doing to the second one, right? Then this thermal energy is going to be transferred over to my chemical energy. So as the particles are moving faster, it's going to transfer some of the energy over into chemical energy, and the reaction is going to occur. And then my chemical energy ends up being higher, and that energy was transferred internally. Notice how it did not go out of the system. It stayed inside. It was transferred internally to my chemical energy. And then overall, and this is how we'll do an LOL diagram for an endothermic reaction, overall, I'll have low chemical energy and thermal energy in the beginning, and I'll have more energy in the ending, more chemical energy in the products. So I would sketch this in your notebook. These are all the steps in the process that you have to know for your unit test. You'll have to sketch and provide this on your unit test having to do with energy. So for an endothermic reaction, I add it to the system, it gets transferred over to chemical, and then I end up with higher energy in my products, in my chemical energy. I'm going to say the exact opposite for an exothermic reaction. So here's an exothermic reaction. A combustion reaction, and we did this in worksheet number 4, question 3, is going to be an exothermic reaction. A combustion reaction is an exothermic reaction. Overall, energy is going to be leaving the system. And if I'm going to exit this. If I want to show you what that looks like, so overall, I'm going to fix this, and you could sketch this. This is what it looks like overall. If you want to see what it looks like overall, I have higher chemical energy before. Eventually, energy will leave the system through thermal energy, and then I'll have lower chemical energy later on. So to start, I'll have, and you can't see it. I have to, I don't know if, let me see. I don't know if you can see it. Oh, that's the overall. I'm going to skip this, right? So again, overall that. So to start, I transfer, this is the very beginning, and you could start sketching this or you'll see the overall one. To start, I transfer some chemical energy over to thermal energy. Nothing leaves the system yet, right? So when reactant molecules collide to produce products that store less energy, new molecules move away more rapidly, okay? So what that means is internally in my system, chemical energy is like potential energy. It's like if I hold a book above my head and I don't move it, it has a high potential energy because I have it all the way above my head, and it has the potential to drop. But if I have the book on the floor, it's got low potential energy. It's probably not going to do anything else unless I kick it, right? And that means I have to add energy to it. So for something that has a high chemical energy, it transfers it over to thermal, and now my thermal energy increases. And then, just like the exact opposite of endothermic reaction, this energy is going to leave the system. These two bars are going to leave the system. It's an exothermic reaction. And then I end up with lower energy in my products eventually. It says products and then it says eventually. So I'll have my products, they'll have like energy, and then it'll be released from the system. And it says eventually my products will have lower thermal and lower chemical energy. Overall, this is what it looks like. And so I want you to sketch this. I move my chemical energy over to my thermal energy. My thermal energy increases, things are hot, and then that energy is released from the system, and I feel it. I feel it as it being hot. And so it'll say something like, the reaction of the beaker feels warm, or a combustion reaction where you see fire or fire occurs, energy is leaving the system. And this is going to be an exothermic reaction. And the way that we draw an energy diagram is the exact opposite of an endothermic reaction. Reactants are going to be higher in energy than my products. And look back, my reactants are higher in energy than my products. Overall, my reactants have more energy. We're specifically talking about chemical energy. My chemical energy is higher in energy than my products, right? And the reactants are higher than my products. So sketching this now for an exothermic reaction, I have higher energy in my reactants. Energy ends up being released, and my products are lower in energy. This is an energy diagram for an exothermic reaction. So overall, just to go back a bit, overall, what you will need to know for your unit test and your final is the way that we write endothermic reactions. So I would write endothermic reaction, write this reaction, knowing that then sketch this diagram for an endothermic reaction, then sketch the overall LOL diagram where energy is absorbed. I have more in my products. Then for an exothermic reaction, I would sketch this reaction. Energy is a product in an exothermic reaction. Then I would sketch the overall LOL diagram for an exothermic reaction where chemical energy is transferred to my thermal, and then it's released. And then I would sketch this exothermic reaction energy diagram where my reactants are higher in energy than my products. Okay, energy is released and my products are going to be lower. All right, so I am done. These were just a quick run through of the slides that we did in class. A combination of this with worksheet number 4 should help you identify how to sketch out LOL diagrams for exothermic and eventually endothermic reactions.